And I will start sharing right away. So, so everybody should be seeing this 3.1 assignment page right now. Um, so I only have that up there just to remind you that was supposed to be the assignment due today. And of course, I will begin with wanting to know how that went. That is, I'm looking for any questions. Hopefully it went smoothly. Hopefully you dug into it. Okay, number 21. We've got a request. We'll take a look at that. Thanks, Camilla. All right, let's take a look at number 21. This was requested. So let me just make sure we get the directions right here in the problem. Number 21 says, in the directions, find the critical numbers and the open intervals in which the function's increasing or decreasing, and then we could check it on a graphing utility. Okay. Before we get started, I want, and it relates to this question, I want to see what everybody remembers about critical numbers. What are critical numbers? And how do you find them? Because that's really where you need to begin this whole issue. So I'd like to get some feedback from you guys on this. So either in the chat, in the group chat, or text message. Yep, that's correct. I did get an answer, and the answer is when the derivative of the function is equal to 0, or when the derivative is undefined. That second part is often forgotten. Now, you're going to see in this problem, undefined is kind of out of the question, because if you look, it's a pretty simple, I mean, it's a nice polynomial function. And so when we go in there to find the derivative, it's a pretty straightforward derivative, right? By the way, I got my pen fixed. Had to get a special battery. And thankfully, at least at this time, everything looks good that way. So anyway, we have a pretty straightforward derivative. There it is, 9x squared plus 24x plus 15. Can that ever be undefined? I mean, we don't even have a denominator. We don't have any roots. So, I mean, that's always going to be defined. So we don't have to worry about that. But we do want to know when the derivative could be 0. So we set it equal to 0, and then we use algebra to try to solve that. When could that be equal to 0? So you can see I began by dividing everything through by 3. It turns out all of the numbers were divisible by 3. That made it a lot more manageable. And then I attempted, I should really have an equal 0 out here. I attempted to factor it. Let's see, did that work out? Let's see, the inner terms, plus 5x, the outer terms, plus 3x. Yeah, plus 5x plus 3x does equal the 8x, so we're good. We got the factors. Set each factor equal to 0. I didn't show that, but when you set 3x plus 5 equals 0, 3x equals negative 5, divide both sides by 3. There's one of our critical numbers when the derivative could be 0, and the other one's real simple. So we have two critical values, negative 1 2/3 and negative 1. Okay, so by the way, I stuck those in so I could find where the points were. This part right here, at this point, you wouldn't have had to do this, okay? I only did that so I could see where those points were. And but do you see where I got this point, 0, 0? I just plugged in 0. No, that's not right either, is it? I'm sorry, in the original function, which you can't see right now. In the original function, if you plug in x equals 0, you would get a 0. So anyway, that's how I got this point. And then I took the two critical values and figured out where their y-coordinates are. We've got this one at -1, -6, and then -1 2/3 is -5 2/3. So I could at least see where, these two right here are the critical values. So I knew something's going on there. The derivative is 0 there, so there's got to be what? A changing direction going on? Sure enough, you can see this one looks like it's a low, and this one over here looks like it's a high. Okay, so we got our fence posts, so to speak, at -1 and -2/3. It's time that, these two guys. So, what happens when we're to the left of -1 2/3? So I chose -2 for that. Something lower than -1 2/3. And when you do f prime at -2, let's see, you can't see the derivative. There it is. So when you do f prime at -2, if you plug that in, you'll get a 3, which is positive. So what does that tell you? Yeah, it's increasing in that left interval. And then we have what? Between -5/3 and -1. And for that one, I picked -4/3. And when I plugged that in, I got a negative. So now I knew it must be decreasing in there. And then I need everything to the right of -1. And a nice, easy one to pick there is what's f prime at 0. Scrolling so you can see the derivative again. There it is. And if you plug in a 0, you get 15, which is obviously positive. So now it's increasing. Now, all you got to do is write the intervals down, which I didn't do, so I'll do that right now. So from -1 on, so this is the interval from -1 to positive infinity, that's increasing. Then we have the interval from -5/3 to -1, and that's where it's decreasing. And then we have everything to the left of -5/3, so we would write that interval like that, and there it would be increasing. And anyway, I included a graph. If we want, we can do it in Desmos, but you can see just pretty much like my rough sketch up there. You can see we analyzed it pretty well. Here's -5/3 down to -1, and sure enough, it is decreasing. And then when we were to the left of that, to the left of -5/3, it was increasing, like it showed up here on the top. And when we're after -1, it again was increasing. So we have pretty much a confirmation. So I know that's a lot of scrolling there. Hopefully, Camilla and anyone else, any follow-up on number 21? No, that's one of our problems from last time. So find the critical points. Then, when you have the critical points, that sets up your intervals. And then just pick a test value in each of the intervals. Find the derivative at that value. Positive tells you the function's increasing in there. A negative tells you the function is decreasing in there. And then pretty much just write down your answer. Other questions from the 3-1 lesson and assignment? I'm hoping that not hearing a whole lot more tells me that you did your homework and really nothing came out too shockingly difficult. All right, at the moment I'm not hearing or seeing anything, so I'm going to go to the beginning of our new lesson. And our new lesson is the one on 3.2 Extrema and the first derivative test. Okay, and you can hopefully see from the illustration here that, I mean, we're looking at the same kind of thing we were looking at yesterday. We want to find when the function's going up, when it's going down. That was the increasing and decreasing we did yesterday. Today we're going to focus more on those critical points where we have what? And let me explain the term here. Why do we call this point here a relative maximum? What we mean is, for that neighborhood of the graph, we're at a high. But overall, you can see we're going to get higher. This point is obviously higher than this one over here. And yet, for this part of for this neighborhood of the graph here, this was a high. That's what we call it, a relative high or a relative maximum. And likewise, down here, we call it a relative minimum because we're at a low valley in the graph, but maybe over here the graph might be lower. So it's not altogether, you know, well, we don't know. I should take that away because, but the point is, you don't, let's see, I'm trying to get the eraser to work here. Let's try that again. So, so if it's in the neighborhood, if it's the low, we call it a relative minimum. Now, look at the whole thing. Which one is absolutely the highest point? This one over here. And so this really is the absolute maximum because it's the highest of all of them. And this one here really is what? The absolute minimum, because if the function starts here and ends here, this is the lowest. You know, that's the lowest point that it will. So we got these new terms. You already know what maximum and minimum mean. But this idea of a relative maximum, the high point of that part of the graph, or a relative minimum, the minimum in that neighborhood of the graph, and then overall, what's the absolute max and what's the absolute min? So we're going to be using those terms. So here we go with some of those definitions. I guess we've really done it already. I don't know if we need to look at the formal definition. I've really gone through that already. So here's a more formal look at a relative extrema. If f has a relative minimum or a relative maximum at a certain value c, then c is a critical number. So in other words, the critical numbers that we learned last time are still important. You should get some kind of a max or a min at a critical number. There's one exception to that, and that's the inflection point, but we'll learn more about that tomorrow. So in other words, the critical numbers are still just as important as they were last time. So here's how you find relative extrema. I mean, you already know this, but here we go. So you got a nice continuous function. Remember, if it's not continuous, these derivatives don't work. If you've got a gap, we're up the creek. You know, it's got to be continuous, smoothly going through. So if it is that, then, I mean, this is pretty, look at number 1. It says, on the interval AB, if the derivative is negative to the left of C and positive to the right, so it's negative to the left, whoops, let me try that again. If it's negative to the left, see, it's going down. So let's just say this is C. It's negative here. It's going downhill, and afterwards it's going, and then afterwards it's positive. Well, then guess what? This point's going to be a relative min. I mean, this is real pretty obvious stuff, isn't it? And number 2 says just the opposite. If it's positive to the left of C, so let's just say this is C. If it's positive to the left and negative after, then guess what? This point is a relative max. So number 3 says, if If the derivative has the same sign to the left and to the right, then it's not. So let me show you what that looks like. Let me extend this page a little bit. So let's say it's positive. Let's say here's x equals c. And it's positive before that. And it's positive after that. Right? The slope is positive in both cases. Then it says that's not a relative extremum. It's not a relative max or a min. It's kind of a what? A resting place. And later we are going to call, and I might have even told you this already, this is called a point of inflection. Even though that's not in this lesson yet, I'm going to throw that in here. We will be talking about that definitely in tomorrow's lesson. Okay? So if you have a critical point, you pretty much have to have one of these three things. Either it's a relative minimum or a relative maximum, or it could be neither, like in number 3, and tomorrow we're going to learn that's called a point of inflection. So it's just kind of a temporary resting spot where the derivative is, where the derivative is horizontal just for a moment, you know. Maybe I didn't draw it right, but it's just for a moment it's horizontal, and then it goes back to positive again. Or, you know, we could have done the same thing with a negative. If this is c and the derivative before it is negative going downhill, and afterwards it's also negative going downhill, then that's not a max or a min, it's a point of inflection again. Okay? So here's some pictures that kind of just, reinforce that. If you look at the picture at the top left, C is a relative minimum. Why? Because it's the low point. We've got a negative derivative on the left. We've got a positive derivative on the right. Obviously, that's a low point. Here, in the second drawing, C is obviously a high point. That's a relative maximum. Again, the derivative coming in is positive, going out is negative. Obviously, we have a high point. And then here are here's 2 points of inflection where it was positive, afterwards positive. That's a point of inflection. It's not a max or a min. And here we have both negatives, another point of inflection. I guess if you want to check, you'll see the book talk about this on page 194. And 194, you'll notice, is in the next lesson. So, just like I said. But pretty hard to not tell you about it because it's part of the picture. So, how does one find absolute extrema? Well, not a whole lot different from what you did for today. You find the critical numbers first. Isn't that exactly what we did today? And then find what the value is at each of the critical numbers. So in other words, find out, at each of its critical numbers, and so this we did yesterday. This is new. Also evaluate the function at the endpoints. You know, at the beginning A and at the end B, and then whichever one is the least, that's the minimum. Whichever one is the greatest, that's the maximum. So almost exactly like last time, except we also want to look at the values at the ends. So I guess let's get in and do an example, and then we can see what we're talking about here. So this is number 1 on the assignment. So got your books handy. This is on page 189. So the function is negative 2x squared plus 4x plus 3, and you're supposed to find all the relative extrema. All right. So step 1, find the derivative. Pretty simple derivative, right? Will that ever be undefined? No. That's just multiplication and addition. That'll always be defined. So Will it ever be 0? Yeah. And you can see there's 1, in this case, 1 critical value, x equals 1. Okay, so that means we divide our function into 2 intervals, everything before 1 and everything after 1. Let's pick a test value. Everything less than 1, how about if we pick 0? What's f prime at 0? Look up here, and you can see it would be 4. That's positive, so now we know that's increasing there. Pick a value after 1, like 2. Plug that in, we get negative, so there it's decreasing. Okay, well, if it's increasing ahead of time and it's decreasing afterwards, then what is 1? That would be a relative max, right? A relative maximum. I mean, let's see, do I have the graph? No. And by the way, that second derivative is, I got antsy, and that's really coming from next time again. So let me just I'll quick open up. Okay, what was our function? Negative 2x squared plus 4x plus 3. All right, so we'll just quick open up Desmos. And negative 2x squared plus 4x plus 3. Oh, now it's pretty obvious, isn't it? If you look right here at this point, you can all see that that's a relative maximum. In fact, it's an absolute max, isn't it? The graph is never going to get higher than that. But for right now, the first question was we're supposed to find the relative max. There it is. There's only one, and it's at 1. So if you want, you can put both coordinates down 1, 5. Okay, so we have a confirmation that's a relative max. Let's go look at another one. Let's look at number 11. Okay, little different directions. Well, yeah, I guess not. It's the same directions. Find all the relative extrema. Okay, well, we have a little bit more complex function this time. It's to the 4th power. And by the way, do you notice? No, they didn't give you an interval, did they? Okay, no interval given. So, start by finding the derivative. Will that ever be undefined? 4x cubed minus 6x squared? Again, there's no denominator. We don't have to worry about division by 0. There's no root, so we can't worry about an even root of a negative. So let's just find out when the derivative could be equal to 0. So we're down to this. Can we factor it? Yeah, actually fairly easily. You can take a 2x squared out of each term. And then, as you can tell right here, set each factor equal to 0, solve. So x equals 0 is one of them. And then 2x minus 3 equals 0, x equals 3/2. So I've got my 2 critical points now. All right? The only thing I'm not sure of is why I use the interval -2 and 2. I guess I just wanted to show an example if they do give you an interval so that you can check the endpoints too. Okay? In example 1, I'm just going to quick look back at example 1. They said use a table. Well, that's pretty much what we've been doing, breaking it into columns. Yeah. Okay, that's what we've been doing. So let's take our 2 critical values, which are 0 and 3/2. I guess I'm going to make a new page to do that. Well, maybe I can fit it in over here. So we've got our two critical values of 0 and 3/2. And that breaks it into three intervals: before, between, and after. Let's pick a sample point to the left of 0. Like I picked -2 up here. Let's pick -1. Okay? So if we pick -1, what's f prime of -1? So just go up to this line right here. What is f prime at -1? Well, -1 cubed is -1. -1 times 4 is -4. And -4 minus 6 is a negative. So this is a negative. So that's supposed to say, let me try that again. So that's a negative, therefore this is decreasing. Okay, let's pick something between 0 and 3/2. Like how about +1? What's f prime at +1? Now we would get 4 minus 6 would be a -2, so that's decreasing again. And now let's pick something bigger than 1/2, like 2. What's f prime at 2? 2 cubed is 8. 8 times 4 is 32. 2 squared is 4. That's 24. -6 times 24 is, well, that's a negative. So this thing appears to be negative forever. So it looks like this thing is forever decreasing. And that's not correct. What did okay, let me check that out again. At 2, what's f prime at 2? 2 cubed is 8. 8 times 4 is 32. 4. Oh, 32 minus 24 is a +8. Sorry. That's what I did wrong. And so, because that's a positive, this last term is increasing. So, from the interval to the left of 0, we have decreasing. Between 0 and 3/2, we have decreasing. Notice it didn't change. That implies one of those resting points. And then from 1 to 2, I'm sorry, after 2, after 1.5, it's increasing. So it finally went uphill. And sure enough, if you look at the function, you can see that's true. It was decreasing. Then it had this kind of a resting point, but it kept decreasing. And then after 1.5, sure enough, it increased. So let's see. So the final thing here is, what are all the relative extrema? Well, this one is not a relative extreme because it kept going down. This one is what? A relative min, because before it was a negative, after it was a positive. So going back up to the problem, this 3/2 point right here is a relative minimum, and that's really the only thing we can take out of this, because all they wanted us to do was to find relative extrema. We found one. It's that one at 3/2. This one right there, right there. By the way, where did I get this y coordinate from? -27/16. Well, just take the x value and plug it into this original function and do the arithmetic. And that's what I did. It turns out to be what? A little bit less than -2. And if you look at the graph, you can see we're not quite down to -2. That makes sense. Okay, so let's go on to another one. Let's go to number 19. Number 19, Here, the only thing different about 19 is this time they do give us an interval. They give us the interval from -1 to 2. So this is what I was anticipating on the last question. So in other words, this time they said, here's your function. Whoops. Here's your function, and here's your interval. Find all the relative, it says find the absolute extrema. Excuse me. Okay, so a little bit different. All right, so first I just multiplied it out. I don't know why they left it that way, but anyway, that's 6 minus 2x. So we find the derivative. It's -2. Will that ever be undefined, -2? No, it's a constant. It's -2 all the time. And will that ever be equal to 0? No. So on this crazy thing, we have no critical points. Well, we can't test the critical points, but we should check the endpoints. Now, here's the one different thing. They gave us this interval, so we need to check what is it at the left of the interval that this is not an ordered pair now, this is an interval. So check it at the left side, -1. Well, if you plug in -1, -1 times -2 is +2, 6 plus 2 is 8. So here's the height of that, and then try it at 2. Plug in. What happens at 2? 2 times -2 is -4, 6 plus -4 is 2. Okay. Well, we have no critical points in between, so here's a rough one. Which is higher, 8 or 2? Duh. 8. So that's the max. And which is the lowest? 2. So that was kind of that was really easy. Okay, so anyway, the only difference when you're finding absolute extrema is I still got to look for the relative extrema. In addition to that, I got to look at the endpoints, and then overall look for which one is highest and which one is lowest. In this case, we didn't have any in between, so all we had to do is look at the endpoints. Let's take one that's a little more challenging that also has some critical points. Okay, Camilla, I'm just finding your comment. That was with that other question. Okay, got it. All right, number 22. Yeah, same thing. We have a function. It's not a very complicated function, and we have an interval, and we are to find the absolute extrema. Step 1, find derivative. Could that ever be undefined? No. 2 times something plus 2 is always going to be easily findable. So the question is, when could it be 0? Well, at one place, at x equals -1. So there's our one critical point. All right? Now this is kind of weird. The critical point turns out to be one of the endpoints. Do you see that? Okay, that doesn't usually happen, but anyway. So, what is the value of the function at -1? So go back up to the top, plug in a -1. -1 squared is 1. 1 minus 2 is -1, and -2 minus 4 is -5. So, and then we got to check it. So this one we've already done just by accident. And now we got to check the other endpoint, 1. What's the function at 1? -1. Okay. So what's the absolute lowest? -5. What's the absolute maximum? It's this point on the bottom. So again, that turned out to be fairly easy. I got to just see. Do we have? Yeah, we got another one that will maybe is what we need to close with, because it'll show you kind of all the scenarios possible. We will have seen them all now. So on number 31, here's our function, and here's our interval. We are supposed to find the absolute extrema on that interval. All right. Step 1, find derivative. Will that derivative ever be undefined? No, we don't have any division, we don't have any roots, so okay, set it equal to 0. Whoops. Let's set it equal to 0. Well, I don't have much hope of factoring that, so you notice I kind of resorted right away to the quadratic formula. Okay, so I mean, I'm not going to calculate that right now, but I came up with these two answers, plus 4.79 and positive 0.31. So you notice right here is where I test those two. What do I mean test it? I mean, what is f of 4.79? In order to find out, you got to go back to the original function, plug in that value for each of these three x's, and do all the arithmetic, and I came up with 4.5. Then you need to do the same thing with 0.31, and you come up with that answer. But in addition, you also have to try these two guys, the beginning of the interval and the end of the interval. So that's why in my list I've also tried 0 and 5. Do you see that? So once again, what's f of 0? Well, that one we can do in our head. If you plug in f of 0, these first three terms with x's in are going to go away, and you're just going to get a negative 3. So that's why we got that. And then plug in 5, cram it, and figure out what it comes out to. It comes out to 7. Okay, so now look at we have 4 y values. 1, 2, 3, 4. Which one's the highest? Obviously this one down here. That's our absolute max. Which one is the lowest? This one, absolute min. Problem complete. So when you're finding relative min and max, it's pretty much what we did yesterday. Set the derivative, find the derivative, see if it could ever be undefined. We didn't have any today that were. But then find out when the derivative can be 0, and then identify, are they a min or a max? So that was pretty much a copy of yesterday. But then, in a problem like this one, where they ask you to find the absolute extrema, you'll always be given an interval. So start off the same way, do your derivative, check if it can be undefined. If not, find out when it can be 0, and that'll give you the critical points. And we got these two, these two critical points. These two. And then in addition, check the endpoints, the 0 and the 5. And that's why the top and the bottom are there. Now, check them all. Go back into the original function, plug and chug, get your y values, and then the last step is really a no-brainer. Just look for the high one and the low one. And that pretty much wraps up the lesson, which was finding absolute extrema. Questions? While I'm throwing out the idea of questions, I'm showing you what the assignment will be. A little bit different. I got 1 to 37, all the odds, but then I threw out 3 problems. We're not going to do 13, 15, or 17. So 1 to 37 odds, but not 13, 15, or 17. So questions, send them my way. Keep this thing live. You can turn on your mic and just ask me a question. That would be very efficient. Otherwise, I'm looking in all these different directions. Got about 5 things to look at. Or you can use the chat or text message, whatever works. questions? Send them my way. I'm not hearing any, so I'm going to wrap this up. Thank you, thank all of you, and hope you enjoy the sunshine today. I'll see you tomorrow.